So in the last video, we saw that we were able to change a particular question from counting a number of customers that arrived at a bank to the amount of time that we had to wait before a new customer would arrive. And this change of counting to measuring, the change from counting customers to measuring time, allowed us to see that we were going to be starting to work in this section with a new continuous distribution, which we call the exponential distribution. Its goal is to describe how much time occurs between occurrences in a Poisson process. So when we hear an exponential distribution ever, we should automatically be associating it with a Poisson distribution. It's kind of almost like they're reverse distributions of each other. We'll see more of how that works in some of the examples later in this section. So the goal of, again, the exponential distribution is to try to judge how long is it going to take before the next thing happens. Now what you'll find interesting here in this box is that I don't actually have any calculator commands for this probability distribution. In fact, what I have instead is a little formula, and we'll practice using this in the examples to come. But there's no fancy calculator menu that I have to go through. I'm just going to be typing in these values into the home screen. I'm still going to have, though, the same value of lambda that we had from a Poisson process, which represented the average rate or average number of occurrences in a given amount of time or space. And I also have here formulas for the mean and the standard deviation of this exponential distribution. Now remember that all continuous distributions have a specific shape. We saw uniform distributions, which were just kind of like a flat line. We had our bell-shaped distribution, which was normal. And my exponential distribution kind of looks something like this. You can see I still have a horizontal number line. It starts at 0 and stretches out towards forever, and I kind of have curves that will stretch downward and then over to the right. They kind of decrease as I move to the right. And some of them are going to be steeper than others. It just ultimately really depends on this value of lambda. You can see here in the picture, if my value of lambda is high, I get a really high curve. If my value of lambda is very low, I get a very low curve. Now, we're going to go ahead and just, in all of our examples, draw kind of like a generic picture of one of these curves. So let's take a look at how we would do that. Let's take a look here at example number 1, and we're going to go ahead and try to see how we can draw a picture, see how we use all this information, and ultimately how all the information here in this box is provided in the formula sheet. Let's take a look here at example number 1. Suppose that arrivals at a bank follow a Poisson distribution with an average of 1.2 customers every minute. This is actually the exact problem that we saw back in the first video. Well, let's see what we ask here. What is the probability of having to wait over 1 minute for the next customer to arrive? Okay, so first I'm going to go ahead and jot down some of the information that I would need to kind of start off thinking through a question like this. And of course, I'm going to go to the formula sheet to kind of follow the flow chart that's presented there. So you'll see over here, again, I'm going to start by defining my random variable, checking out my distribution, going through my checks, writing my parameters before I start computing any probabilities whatsoever. So let's start with the random variable. We already kind of defined this variable up above, but I'll go ahead and rewrite it here. We'll say, let y represent the amount of time it takes for the next customer, to arrive. Okay, so this is what we want to measure, right? Like, how long does it take? So let's say y is that amount of time. Well, again, since we're interested in measuring the amount of time it takes for the next occurrence to happen, that is an exponential distribution. So we can say y has an exponential distribution. And again, if I want to go ahead and just double check to make sure that I'm right, notice that the formula sheet says that occurrences of events need to follow a Poisson process. And we actually have exactly that here in the problem, where we're told that customers show up at the bank following a Poisson process. So we know that this is going to be an exponential distribution, and we know that it's going to have an important parameter, again, listed on the formula sheet. We see that that parameter is lambda, just the same exact lambda that we would have had in exponential. So I'm going to go ahead and write down this lambda to see what we come up with. So lambda was told to me here as a value of 1.2. And I'm going to highlight right now that this is customers per minute. So this is customers per minute. And that unit of time we're going to see is actually super, super important. So I'm going to go ahead and I'm going to start to draw out a little picture of what I'm looking for. So I'm going to draw a picture of an exponential distribution. Okay, so my exponential distributions look something kind of like this. Okay, they go like that, and zero's right over here, and I'm interested in a probability of the amount of time I have to wait being over 1 minute. Now here comes the most important part of everything in this section, like most important part of section 5.3 is if I'm interested in having to wait over 1 minute, I need to make sure that the unit of time in my lambda is also minutes. If it's not, I'm going to be in trouble. But since these two things match right now, everything's going to be super easy. So notice down here on my number line, I'm going to write down that y right now is indeed being measured in minutes. It's the amount of time. We're going to measure it right now in minutes. So when I say I want to wait over 1 minute, I can imagine putting 1 minute in the picture, and then I can go ahead and shade over it, just like we've done in all the previous sections. Now I want to find that probability, but how do I do it? Well, if you take a look at what the formula sheet says, or the box up above, you can see that in order to calculate the chances that x is bigger than some number, you have to take e, and let me zoom in here so we can see this easier, but I have to take e, I have to raise it to the power of the opposite of this value, and then multiply by lambda. Okay, so let's see what that looks like here. In our case, we're going to have to go ahead and take the value e, raise it to the opposite of the value we want to be bigger than, and then multiply by my value of lambda. So notice this is going to be e to the power of negative 1.2. Okay, so if I wanted to compute my final probability, I would just have to go to my calculator and just directly type this in to see what I come up with. So let's switch over to our calculator and see what we get. Okay, so when I switch over here, I can go ahead and find now my value of e. You have two different spots for it on the calculator. You might recall that it exists above this natural log button in blue or in yellow, but also above the division sign you can have an e. I'm going to go ahead and use the one that's down here next to natural log because it already provides me with an exponent. And I know I want to type in negative 1.2. Now if I hit enter, I get a value back, 0.3012. So I'm going to go ahead and write that down, 0.3012. And that's my probability. The chances that I have to wait over a minute, 0.3012. Okay, so this should hopefully give you a good idea of how I actually can use the exponential distribution to calculate some probabilities. And in the next video, we'll go ahead and look at kind of the remaining parts of example number 1 to see how some things might change, and we may have to adapt this probability formula that we've seen here.